So let's imagine we have an object going around in a circle. Okay, so it's got some mass m. Now we know that there's a force on it that makes it go around, centripetal force, and that's going to be mv squared over r. Well, we know that v equals r omega, so this could be m r squared omega over r. Okay, or it's mr squared omega squared over r, or mr omega squared. But let's remember this form right here for just a second here, because the other thing is kinetic energy. Okay, so we got kinetic energy. What's the kinetic energy of this motion? So we've got kinetic energy, and we know the kinetic energy is just 1/2 mv squared. And so if this thing's moving some velocity v, it's going to have a kinetic energy. Well, once again, we could rewrite that as 1/2 mr squared omega squared. Now notice when we had the centripetal force, we had mr squared omega squared over r. Okay, so we have this mr squared in there. Okay, and so that's an interesting sort of thing. Now, if I want to make the thing accelerate, I'm going to have to exert a force on it. And so the force is mass times acceleration. And so that's going to be equal to mr alpha. Well, this is the interesting thing, and that is that if I multiply both sides by r, then I get that mr squared back again. And so we keep getting this mr squared, and we think about it and say, well, if I have like two masses, you know, like I have a massless CD or DVD or something, got two masses going around it. One of it is some radius r1, one's at radius r2. So we have m1, m2. So we got m1 r1 squared plus m2 r2 squared. Okay, so the kinetic energy is going to be 1/2 that times omega squared. Okay, and likewise, if I want to make this thing accelerate, if I exert a force here, imagine they're both connected somehow. So in other words, imagine I have something that has two things here, you know, it's rotating around this axis right here. If I push on one, they both get moved. And so I want to accelerate both of them. So the force is not just a force, because that just acts on the one, but if I have r times f, that's going to be the sum mr squared times alpha. Okay, and so because the alpha is going to be the same for all, and they all run together. And so what you end up with, that you really end up with this really interesting idea, and that is that mr squared, or if you have a whole bunch of things going around, different m's at different r's, the sum of the mr squared, okay, falls into the equations. We're going to just use the letter I to represent that. It falls in all the equations the same way that m does. So where we used to have, you know, that kinetic energy is 1/2 mv squared, we now have the kinetic energy is 1/2 I omega squared. Where we used to have, for example, centripetal force is mv squared over r, we now have centripetal force is I omega squared over r. And you know, and then you can extend this one more. You know, we had F equals ma. If we replace, you know, the a with alpha and we replace the m with I, we have r times f, and so we give that a letter tau. We'll get back to that later. It turns out that tau is torque. Okay, so where we used to have x equals x naught plus v naught t plus 1/2 at squared, we now have the theta is theta naught plus omega naught t plus 1/2 alpha t. Okay, now notice what's happening in all these equations. Wherever we used to have an m, we now have an I. So the I is like the distributed mass. So if the mass is farther out, it takes more kinetic energy and more torque to make it move than if the mass is in close. Okay. Wherever we used to have a V, we now have an omega. Wherever we used to have an X, we now have a theta. Wherever we used to have an A, we now have an alpha. Notice the relationship here. We used to have an F, we now have a tau for torque. So torque is like the rotational force. So the torque, a way of thinking about torque is, the torque is, it tells you how the force relates to this. So torque equals I alpha. Well, think about these equations. You know, we used to have work is force times distance. So what do you think work is going to be in angular terms? Well, wherever there used to be an F, we have a tau. Wherever we used to have an X, we have a theta. So work or change in energy is going to be torque times angle. So once again, this kind of makes sense, because F equals ma, right? Okay, and then we have X, and so we have m r alpha and r theta, so m r squared alpha theta. Okay, so this is what this gives us, but that's what this gives us. Okay, because torque is going to be I alpha, so that's I and that's alpha. Okay, so all these equations work out, and so this is the really cool thing about the rotational dynamics, and that is there's nothing new to learn. You just have to remember, where there was an X, we have a theta. Where there was a V, you have an omega. Where there was an A, you have an alpha. Okay, where there used to be a mass, the equations now have I, and where there used to be, for example, a force, the equations now have a torque. Okay, we're going to later figure out where there used to be P for momentum, there's now going to be L for angular momentum. Okay, so again, P equals mass times velocity, so what do you think angular momentum is? Well, just look over here to the left. Where there used to be an M, there's an I. Where there used to be a V, there's omega, angular momentum. Okay. And so this kind of gives you an idea. There's nothing really new. So if you can remember that for the dynamics, rotational dynamics, all you have to do is make that type of substitution in there, then all of a sudden that makes this a vastly easier problem to handle. So now it becomes pretty easy to figure out things and figure out how to use the equations. Now, I will admit, there's a slight issue if you're trying to find I of a distributed mass. So in other words, if it's not discrete masses at different R's, then it becomes more complicated to do the mr squared. Okay, so that'll be the next lectures. What do we do for an extended mass? But that's the only hard part, is figuring it out, and then everything else is just straightforward and easy.